Okay. Well, again, happy Halloween. Today's lecture we are going to take just a look at some basic statistical ideas when it comes to. We'll start with comparing groups, and then we'll kind of expand from there. Um, I hope you guys have met with your group projects. With your groups, and you're searching for data or kind of discussing data things. And again, if your group hasn't signed up for a proposal time slot, please sign up for a proposal time slot and work on that questionnaire. And anyway, but as you guys start getting working on your group projects and you start doing your analysis, okay, there's going to be a time where you're going to transition from just kind of exploratory and descriptive statistics into what we call statistical inference. Okay, and kind of the central idea here is we want to try to decide if what we're seeing in the data is just a random fluke of our data, or if it's actually indicative of things that are different in the population, or whatever it is we're trying to generalize to. So this is I've just made up some fictional scenario, okay, and I don't know if you guys have wondered this, but you go to like Target, and they sell like store brand batteries, right? And then of course there's also like the name brands. Energizer, is that right? Right, so you have like name brand batteries, and what's the other one? Duracell. Okay, these are probably like the big name brand batteries. And then you have like the store brand batteries, and the store brand batteries are like way cheaper, and you're like, well, can I just save money? Is there actually a difference? Right, this is what I'm curious about. Okay, and let's say somebody says, you know what, they're all the same. Okay, um, and actually, or maybe you just want to know, like, is there a difference between like Target's battery and Walmart's battery? Are they actually just the same battery but just different stickers on them? Okay, so you say, well, let's do a test, right? And so you decide to run an experiment, okay, and you collect data. And so you build like this little contraption that's, you hook the battery in and it drains the battery at a constant rate, and then you kind of test how much voltage the battery has. And a lot of times batteries will start at 1.5 volts, and actually when it I don't know how they work, but there's like a chemical thing, and basically once it's kind of run through that, the amount of voltage it's able to produce goes down. And so a lot of times by the time the battery is only able to produce 1.35 volts, it's rarely like zero, okay? But like once it drops down to a certain thing, you're going to say like the battery's dead, okay? It's no longer functioning at its supposed thing. So anyway, you have some machine, and you measure how long it took based on the load. So we load up this thing. This is all fictional data, by the way. I didn't actually run the experiment. We're going to just pretend we have this. And I think I've uploaded this fake batteries CSV file. It's also, well, anyway, it's there if you want to play along, okay? And so this data just comes in. It just comes in like this. I've got brand A, I've got brand B. I just did 12 batteries on brand A, and this is how long they lasted. 12 batteries on brand B, and this is how long they lasted. Sometimes the data comes in this form. This is actually not the form we would want, because this is not like, what do we call it? It's the rows don't actually provide any useful structure. Okay, so we would say this is not in tidy form, because in tidy form, each row represents an observation, and here the rows don't actually represent anything. This is just like one arbitrary battery from brand A, and this is a different arbitrary battery from brand B. It's not like this is a person that got measured under one condition and got measured again under different conditions or something like that. So I could just as easily kind of scramble up the order in the second column, and I wouldn't lose any actual information. Okay, so what we would do is I'm going to pivot the data, right? And so what am I going to do? If I want to get both of these values into one column, we're going to say we're going to pivot them longer. Okay, so I'm going to pivot the column brand A and brand B. I'm going to pivot them longer, and then we need to take the column headings, brand A and brand B, and that we're going to create a new column called brand. So we're going to have two columns now. We got brand and runtime, okay? And then we have brand A 135. And so now this is in a better form in that each row just represents a separate observation, okay? So each row is a separate observation, and I can take this and create a plot or whatever. My plot got messed up. Let me run this. Did I ever talk about box plots? No? Or I did. Okay. Because I can't, sometimes I get confused. I mean, a lot of times. Let's see. Let's run this. Okay, so here, it doesn't exist. The batteries. All right, so here we go. So we have brand A's runtime, and its median runtime looks like around 121, and brand B's median runtime is around 130 something, okay? And the question is there a significant difference, okay? Like, so based on this, if you're just going off of median runtime, like if I just take brand A's, so if I have my batteries, okay, and I wanted to kind of do a summary operation, what would I do? I would do something like, okay, so there's a few ways you can do this, right? You can take batteries and you can filter so that brand equals brand A. Okay, and so then we get those values, and then we would take select runtime and pull it, and then we would calculate the mean. Okay, so I have those values, and then I could say, hey, calculate the mean there, right? And so the mean runtime there, or the median maybe. So the median of brand A is 121, and I can do the same thing for brand B. And I get 131, 121 versus 131. Okay, the other is, and my recommended method would be like group by. I would group by the brand. And then we're going to call summarize and say I want to say the median is going to be found by taking the median of runtime. Okay, and so we get brand A's median runtime is 121, brand B's median runtime is 131. Okay. So anyway, the question is, in my data set, where I have these 12 batteries from brand A and the median runtime is 121, I got 12 batteries from brand B and the median runtime is 131. The question is that, oh, okay, I guess, and if you look at the mean, Okay, 123 and 129 instead of medians. If you're looking at the means, we get 123 and 129. The question is that difference significant? Okay, so if I say, hey, what's the average runtime for brand A? The average is 123. What's the average runtime for brand B? It's 129. And so you go, okay, so that's a 6-minute difference. Is that actually reflective of a difference between the quality of the brands between brand A and brand B? Or could it just be that my batch of 12 batteries for brand A just happened, because not all batteries are exactly the same, or maybe the conditions were slightly, I don't know, maybe the temperature was slightly off, I don't know. And so if I selected another 12 batteries from brand A, is it possible that I would get 129? And then if I select another 12 batteries from brand B, I would get 123. Is that possible? Or is this actually indicative of there actually being a difference between our two brands? Okay, so this is kind of the underlying question for a lot of what we do in statistics is, hey, I'm noticing a difference in my data, but is that difference actually a big deal? Okay, it's kind of like another example I like to use is, I don't know if you ever play board games where you roll dice. And so I don't know, there's a game called Settlers of Catan. I don't know if you've played, but you roll dice, and based on basically what numbers show up, you like collect, rocks or something, okay? And so you might pick certain numbers, and as you're playing the game, it feels like your numbers never get rolled, and like the other players, their numbers get rolled. And so you might complain, something's wrong with the dice, okay? Because it's like, oh man, we keep rolling the number 6, but I'm never getting the number, I feel like I should be getting the number 8, right? That's my number. I want to see the number 8, and I'm not seeing the number 8, but I keep seeing the number 6, and that's not helping me. And you go, oh, I think something's wrong with your dice, okay? And that's like a fair question. Maybe there is actually something wrong with the dice, and we have to buy new dice because something's wrong with them. Or maybe we just have bad luck, okay? And that's kind of, we can use statistics and probability to try to answer that question. And we would do a statistical test and say, okay, well, let's actually count how many times we see the number 6, and let's count how many times we saw the number 8. And is the number of times I'm seeing it outside the range of like what randomness would account for, okay? And so here's kind of the question. All right, let's look at our data. We got 123 and 129. That's a difference of 6 minutes. Is that difference of 6 minutes outside the range of what we would consider like normal fluctuations and normal variation? Or is it kind of like within, some variation is okay, right? So, it's like you go to the doctor and they measure your blood sugar or your blood pressure or whatever, and they say, hey, it's a little elevated, but you're still within normal, so we're not going to raise any alarms. But then if it starts getting too high, you go, oh, maybe you need to start taking some medication or something, okay? And this is kind of our question. Brand A's average is 123, brand B's average is 129. We're seeing a 6-minute difference in our sample of data. What does that say about the corresponding population? We talked about samples and populations earlier in the week, okay? And so the question that we're really trying to get at is not like, what am I seeing in my data? I mean, this is interesting, but we really want to know, okay, I'm seeing a difference of 6 minutes here. Is that indicative of an actual difference in the population between brand A and brand B, actually different? Or could it just be a random fluke? Could it just be a little bit of bad luck? Brand A had bad luck in that the 12 batteries I happened to pick happened to be slightly lower performers, and brand B had good luck, and the batteries I selected happened to be good performers. That's kind of what we want to know. Like, how much can we say there, okay? So we want to distinguish between actual phenomena and random variation. And so just Other examples, you know, if you flip a coin 20 times, what you expect is you expect 10 heads and 10 tails, okay? What if you flip a coin 20 times and you only get 5 heads, okay? Does that mean something's wrong with your coin or your flipping technique? Or could it just be that you had some weird random luck, okay? You know, this becomes a little bit more important in like medical cases. You're testing out a new drug, okay? And you want to know, okay, is this actually improving? So in one case, with the medication, you get improvement in 65% of patients. And the other, when you give placebo, you also improvement, but it's only 55%. And so is that 10 percentage point difference, is that, can we say, yeah, the drug is more effective than placebo, okay? Or is everything just placebo effect, okay? Is it, you know, is it just that we happen to get a little bit more placebo effect and we got more improvement with the people who got the medication, okay? And so we run hypothesis tests to try to do these things. Okay, let me, before I forget, this is Friday. Okay, are you guys taking bets on what letter it's going to be? The first letter is D. D as in dog. D. Okay, so the way we ask these questions and try to answer them is using a hypothesis test, and we can think of this as kind of a logical framework, okay? A logical framework for us to draw conclusions as we think about our data, okay? And so we're going to start with one of the most basic hypothesis tests, and this is called the two-sample t-test. And technically what we're doing is going to be called the two-sample Welch t-test, if we want all of this. But basically, it's if you have two groups, and you have a mean of group 1 and a mean of group 2, or a mean of group A and a mean of group B, and you want to know, are these means different? Okay, we have different tests for different scenarios. So if you have like categorical data, then you're going to calculate a proportion, and we have a different test for that. But in this case, we have numbers. We've got a mean of group 1 and a mean of group 2. We want to compare those means. And so as we do this, the question that we want to answer, we have to state it as a testable hypothesis. And we call this thing the null hypothesis. And in kind of this, in maybe a little bit of counterintuitive sense, we're a lot of times we're hoping to prove the null hypothesis wrong. We're like hoping, so we start off with this hypothesis and we're kind of like hoping to reject it or say that, yeah, I got enough evidence to prove it wrong, okay? But we start off with the null hypothesis. We test the null hypothesis against the data we observe, okay? The null hypothesis, in order for it to be testable, it has to be a specific claim about the population, okay? If it's not specific, if it's super vague, you can't disprove it, okay? And this is just kind of like any other kind of statement. You know, if somebody makes a vague statement, you can't disprove their statements. But if they say, hey, this is going to happen at this exact time and it's a very specific thing, then you can see like it's either going to come true or it's not, okay? And so as far as this, we start off with a very specific claim, and what we're hoping is that we have enough data to kind of reject that claim, okay? And so as far as the t-test goes, almost in a counterintuitive sense, we say the null hypothesis is that the two means are equal, that population 1 has this mean, mu1, population 2 has mean mu2, and those two numbers are the same. So in the case of the batteries, we're going to say, yeah, you know what, brand A and brand B, they're really the same battery. Okay, they just changed the stickers, but underneath it's the same battery. If you look at the average of brand A, it's going to be mu, this number, and if you look at the average of brand B, it's the exact same number. That's what our null hypothesis is stating. Okay, so the null hypothesis says is your two averages. The symbol we use for the average is mu. Okay. Looks like a U, but it's like the mu, the mean of group A is the same as the mean of group B. That's the null hypothesis, okay? And then the way we test it is we take this hypothesis and we say, let's pretend it's true. Let's pretend this statement that brand A and brand B are actually the same. Let's pretend that's true, and if it were true, what would my data look like? What does the world look like in this scenario, and what would my data look like? Okay, so we say, let's assume the claim made by the null hypothesis is true. And so we take this hypothesis and we imagine kind of this hypothetical scenario where the hypothesis is true, okay? We say if brand A and brand B truly are the same and they have the same mean, then what my data should look like is that when I take a sample from brand A and I take a sample from brand B, I should be getting pretty much the same mean if that null hypothesis were true, okay? But I also know there's some randomness. I'm not expecting it to be exactly the same, but if it's true, I should be getting something similar, okay? So I look at my data. My data actually has a mean of 123, and brand B has a mean of 129. So I'm getting a difference of 6 minutes, okay? And so the question is that difference of 6 minutes, is that different enough from 0 for me to say that's a big deal? Or is it not that big of a deal, okay? That's kind of our question, right? I'm expecting the difference to be around 0, right? If this null hypothesis were actually true, brand A and brand B are the same, in the long run, if I take a whole bunch of samples of data from brand A and a whole bunch of samples from data from brand B, I would expect overall a difference of 0, okay? But it's random, so maybe sometimes I get some good batteries and sometimes I get some bad batteries. Right now I'm getting a difference of 6. The question is that a big deal, okay? So, okay, so that's basically what this whole slide says, all right? So we want to know if they do actually have the same mean, what's the probability that just kind of by randomness, I happen to get some lower performing brand A batteries and higher performing brand B batteries where I'm getting a difference of 6, okay? What's the probability of something like that happening just kind of by random chance and random coincidence if they actually were the same, right? It's kind of like if you actually did have a fair coin, is it possible that just by random chance you flip only 5 heads and 15 tails? It could happen. How often does it happen? Not too much, okay? And so we kind of, but we want to figure out that probability, okay? And so that probability, we call it the p-value, okay? And so the p-value is, what's the probability of getting the number we see in our data, okay? We see a difference of 6 minutes, or I'm seeing only 5 heads out of 20 flips, okay? What's the probability of that happening just kind of by randomness versus the populations are actually different or my coin is actually unfair, right? So we're saying, what's the probability of seeing a difference of 6 minutes if the two brands actually have the same mean, okay? And so we're going to go through a bunch of calculations, and that probability could either be a big number or a small number. We're just going to, and so let's just think about what it means if that number is small, okay? If we go through our calculations, and our calculations say the probability of this happening by random chance is really small, okay, then that would provide evidence that our data is not the result of random chance. Okay, it's a little bit, it feels a little bit strange, but it's kind of like saying if brand A and brand B actually are the same, yes, random chance could explain some differences. But according to random chance, we probably should only see differences of like 3 minutes. And we're seeing a difference of 6 minutes, okay? So therefore, the difference we're seeing of 6 minutes can't really be explained by random chance, okay? It has to be like this really weird thing to happen for us to get a difference of 6 minutes. And so the fact that I saw a 6 minute difference means that I don't think brand A and brand B are the same. Okay, there's in another way, let's go back to this coin flip thing, okay? When I flip the coin 20 times, I'm expecting some random variation, okay? Sometimes I get more heads, sometimes I get more tails, okay? Let's say the coin lands heads only twice and it landed tails 18 times, okay? Is that possible by just randomness? Is it possible by just randomness to get only 2 heads and 18 tails? Okay, it's not impossible, but it's really, really, really unlikely. Okay, and so if that actually happened, I flipped the coin 20 times and I only get 2 heads and 18 tails, either I have to say, wow, this is some really incredible luck that I'm getting, or perhaps the easier conclusion is something's wrong with my coin, and that's why I'm getting only 2 heads. Okay, and in that case, we'd say, yeah, probably something's wrong with your coin or your coin flipping technique. That's an easier explanation than to say you're seeing this 1 in 1,000 situation, okay? And so maybe we do our calculations and it says, could you get a difference of 6 minutes by random chance? Yeah, it could happen, but it's like 1 in 100. And so we say, okay, either I happen to be that lucky 1 in 100 and that's why I'm seeing 6 minutes difference, or maybe the easier explanation is that brand A is worse and brand B is better, and that's why I'm seeing a difference of 6 minutes. Okay, so that's one potential outcome. Yeah, question.
When running these statistical tests for our products,
yeah,
do we choose our own alpha levels?
Yeah. I would say overall rule of thumb 5%, but yeah, we'll talk about alpha and all of that. Okay. The flip side, okay, is that maybe you do your calculations and the p-value is large. Okay. And so let's say you do your calculations and it says, hey, you know what? 6 minute difference, not that big of a deal. Okay. Yeah, when you do random sampling, sometimes you get big numbers and sometimes you get small numbers, and getting a difference of 6 minutes, not that big of a deal. Okay. Yeah, it's not 0, but also it's not that unusual. And therefore, if it's not unusual, you would say we have no reason to really believe that our 2 means, mu A and mu B, are different, okay? It doesn't mean that the 2 are equal. It just means you don't have enough evidence to kind of say that they're different. So again, it'd be like if you flip the coin 20 times, let's say you get, you would expect 10 heads and 10 tails. But let's say you only get 8 heads and 12 tails, okay? And then you ask your question. Could a fair coin produce only 8 heads and 12 tails? And the answer is yes. A fair coin, just by random luck, can produce only 8 heads and 12 tails. And something like that is actually going to happen quite a bit. It's going to happen quite a bit, like maybe a 30% chance of something like that happening. Okay? And so therefore, if that's what your data is, 8 heads and 12 tails, you're not going to suddenly suspect that your coin is unfair. Does it prove that your coin is a fair coin? No, it doesn't prove your coin is a fair coin. But 8 heads out of 20 flips is not weird enough for you to say something's wrong with my coin. Okay, and so that's another possibility, right? Maybe we do our calculations and say 6 minute difference is not weird enough. Okay, but we have to do our calculations to decide if a 6 minute difference is weird and unusual circumstance or if it's not. Okay, and that level, okay, whether our p-value is big or small, okay, because the outcome is either p-value is small or p-value is big, is determined by what we call the significance level, or alpha. Okay, and so rule of thumb, a very common choice is we use 5%. If the probability is less than 5%, we say, hey, it's a small value. And if it's bigger than 5%, we say it's not a small value. Okay, this is a very arbitrary number. It's a reasonable number, but I think, a lot of it's probably because we have 5 fingers on our hand, which I'm grateful for. But a lot of times we just kind of pick these arbitrary numbers, right? And so, yeah, if we say alpha is 5% and you get a p-value that's less than 5%, we say it's small. And therefore, I don't think my results were just random luck. And I'm going to reject the null hypothesis. And if the p-value is greater than alpha, our p-value is going to be considered to be large. And we'd say, even if the null hypothesis were true, the data we've considered is not an unusual result. And so we don't have reason to believe the null hypothesis is wrong, and we don't reject the null hypothesis. Okay. If this is the very first time you're seeing a hypothesis test, there is kind of it's a lot of kind of logical thinking to kind of wrap your head around. And all I can say is encourage you to just kind of review these things. I've tried to explain it as best as I can. But yeah, there is a kind of a logical framework as far as how we think about it and make our conclusions. And it takes a while to get there, especially if it's your first time. So what I'm going to do is I'm going to take my data. I have 123, 129. I've calculated some other summary statistics. You can take these numbers and plug them into a t-test. We can run R and do our calculations. Okay, so the formal hypothesis test, our null hypothesis is that the two means are the same, and the alternative is that the means of the populations are different, that brand A is actually different from brand B, whereas the null is that brand A and brand B are actually the same, we just have different stickers. Okay, and so to conduct the test, the operation we use is we take the vector of values and we throw them into t.test. So to kind of extract these values, I run this code. I say filter to the brand I want, select the column of values I want, and then pull them, extracts them as a vector. Versus if you don't call pull, you just get back the entire table. Or you get a table and it's a table with one column and a little bit annoying to work with. Pull extracts it as a vector. I do the same thing for brand A and the same thing for brand B. I have these vectors of values, and then I say do a t-test. Compare brand A with brand B. And so this is the Welch 2-sample t-test. That's kind of the full name of this thing. And this is the output. So we're not going to worry about all of the math behind it, okay? And it calculates a few things. It calculates a t-statistic, which is why it's called a t-test. It calculates the degrees of freedom, and then the important number that we need is the p-value. The p-value is the probability of getting a difference of 6 minutes. And it says, if brand A and brand B actually did have the same mean, and you took 2 samples of size 12, okay, could you get a difference of 6 minutes? Yes. How often does that happen? Around 9% of the time. That's what this p-value is stating, okay? Saying it's around a 9% probability. So it's kind of like, if we're picking random numbers, okay, from the same population, this is what the null hypothesis says. The null hypothesis says brand A and brand B, they're actually the same battery, okay? If you just pick 12 random numbers and you calculate the average, and you take another 12 random numbers and you calculate the average, you might get a difference of six points. How often does that happen? It's not super common, but it happens around 9% of the time, okay? And so that's what we're seeing in our data, okay? We're seeing a difference of 6 points, and we can say, well, maybe I was just part of the 9%, okay? And therefore, I'm not ready to come to the conclusion that the two brands are actually different, okay? It's quite possible. There's like 9% of the time, when you take random samples, you're going to get a difference of 6% or 6 points, okay? Our threshold for whether it's big or small was 5%. 9% is over 5%, and so that's why we're saying our p-value is large, and we come to the conclusion not to reject the null hypothesis, okay? The p-value is over 5%. It means the data we have could have been produced by randomness even while the null hypothesis were true, okay? So all that to say, based on the data we've collected so far, we cannot make a definitive conclusion, okay? One, it's possible that brand A and brand B are actually the same product, just different stickers, and this 6-minute difference we're seeing in our data is just random coincidence, okay? Another possibility is that we just don't have enough data, okay? Maybe they actually are different. Brand A comes from one factory, brand B comes from a different factory. They actually are different batteries, okay? And we're seeing a 6-minute difference because they actually are different. It's just, I only have 12 batteries from each brand, so that's not enough to really draw a definitive conclusion, okay? So all we can say is just, I don't have enough evidence to say they're different, okay? Our decision is not to reject the null hypothesis. I don't have enough evidence based on having only 12 batteries each to come to that conclusion. Okay, let me give you your second answer. Second answer is C. C as in cat. C as in cat. Okay, one important thing, never use this phrase, we accept the null hypothesis, okay? We did not reject it, okay? And in day-to-day language, when you don't reject something, it means you kind of accept it. But in statistics, these are distinct things, okay? We didn't reject the null hypothesis, but that doesn't mean the null hypothesis is true, okay? We can't say having only a 6-minute difference means brand A and brand B are the same. It's just 6 minutes is not enough for us to come to the conclusion that they're different, okay? Let's say we go out and we collect a lot more data, okay? So now I get 36 batteries from brand A, 36 batteries from brand B, okay? And so here I make a big vector for brand A and big vector for brand B, okay? And so these are just a lot more batteries. And then so let's say after I collected 36 batteries from brand A, the average is 123, and I get 36 batteries from brand B, the average is 129. So we're still only getting a 6-minute difference, but now I have a lot more data to kind of back this up, okay? And so when I do a t-test here, okay, t-test, I've got that brand A, vector of brand A, and vector for brand B. Here, my p-value is only 1% now. My p-value is a lot smaller, okay? So again, I got 36 batteries from each. I'm seeing the same 6-minute difference, but now my p-value is only 1%, okay? So what does this mean? This means that if my hypothetical situation is actually true, that the batteries are coming from the same factory and we're just swapping stickers, okay? You know, could I just by random luck select 36 batteries that just by random luck happen to have an average of 123 and another 36 batteries where the average happens to be 129 and we're getting a 6-point difference or 6-minute difference? Could that happen just by random luck? It could, but how often does that happen? It's pretty rare. It happens only 1% of the time, okay? And so the easier conclusion, rather than saying, oh, you must have gotten really lucky with that 1%, okay? The easier conclusion is, oh, these aren't coming from the same factory, okay? That they actually are different, okay? And just a comparison. Let's say I was doing a card trick, and I say, hey, name a card. And you say 7 of diamonds. And then I reach in the deck and I pull a card out, and it's the 7 of diamonds. Okay, I think that would be impressive, right? You could say, oh, you just got lucky, right? Because it's true. If I pull a card, if I do this trick, I will get it right on average 1 out of every 52. Okay, on average, if I just pull a random card, I'll select your card 1 out of 52 times. Okay, so it's possible. Was I just lucky and I got it right 1 out of 52? Okay, you could dismiss it as that, but probably it would feel impressive, and you go, oh, how'd you do that? Okay, and the same kind of thing. Is it possible that just by random weird luck I got a difference of 6 points? I got 36 batteries over here and a 36 batteries over here, and the difference ends up being 6 minutes? It could happen, but it happens pretty rarely. Something like that happens only 1% of the time. Okay. Yes, we acknowledge randomness is a real part of life, but stuff like this just doesn't happen very often. And so, because randomness would only produce this around 1% of the time, okay, and this actually happened here, I have to come to the conclusion I was that lucky 1%, or maybe the easier explanation is that the batteries are actually different. And that's why I'm seeing a difference of six minutes, okay? And so I would say if your p-value is only 1%, the easier conclusion is to say, the reason why we're seeing 6 minutes difference is because the batteries actually are different. These 36 batteries over here are coming from a different factory. These 36 batteries over here are coming from a different factory. That's why we're seeing a 6-minute difference, okay? And it's not that we just happen to get some random sample that happened to perform poorly and a different random sample that happened to perform better, okay? So in this case, the p-value is small, and so that means this difference of 6 minutes would be considered extreme and unusual if the null hypothesis were true, okay? So if brand A and brand B did come from the same factory, it would be quite unusual, okay, of getting this. It's not impossible, but it only happens 1% of the time. And so with a small p-value, our decision is going to be to reject the null hypothesis, okay? And we conclude the reason why we're seeing a difference of 6 minutes is because the two brands actually are, in fact, different, okay? So that's kind of the big thing. What did I put for additional notes here, okay? The hypotheses are always statements about the population, and we can have directional things. All right, so maybe I'll talk about these things later. But this is just to start getting you to start thinking about, hey, I'm noticing a difference. As you're doing your exploratory data analysis and you do things with the tidyverse and you say group by this variable and calculate the mean of this group and the mean of this group and the mean of this group, you're going to start seeing differences, okay? And then I want you in the back of your mind, is the difference I'm seeing actually reflective of differences in the population, or is it possible that it's just random, like a random fluke that's producing this difference, okay? All right, that's it for today. Oh, last view quiz answer is the letter E. E as in elephant is your third view quiz answer. We'll go ahead and wrap up here. Have a great rest of your day. Have a happy Halloween. Stay safe. We'll see you Monday.